So when we talk about binary number system, binary and hexadecimal number systems are the most prevalent in computer science, and binary essentially creates the base for our computation that we do today, especially in digital electronics. So this is because in transistors especially, we have to indicate on by 1 and off as 0, because this is the most prevalent method, and as per this method we have to use binary to represent numbers, and then using these numbers we can have our own encoding for language and so on. So binary is essentially at the base of all computation we do today, and hexadecimal is just a more compact form to just write the 32-bit and 64-bit binary numbers in a more compact form, because four different binary numbers can be compacted down to a single hexadecimal number, and we cannot input this into the computer directly or the embedded system or whatever, but for it is more human readable. For example, we write in binary 0b0000, and that is a very long number to read. However, if we have to read out this hexadecimal number, we can just read out 0x3a 3a21. So that is what we have to read out if we have to refer to it in a human readable form. So this is why we use hexadecimal notation. So this is essentially a notation. Nothing especially changes in the real world if we start using duodecimal or hexadecimal instead of decimal. Well, we use decimal in our daily lives, and the notation we use is that, let's say we are representing 78, then we do not have to write this when we are doing some normal arithmetic. But if we have to signify that this is not in, just remove this for now, if this is not in the decimal number system, we have to write the radix r here. For example, it may be 12, or it may be it cannot be binary because we are already exceeding the numbers beyond 1. So it could be 9. The radix could be 9. What that would mean is that instead of having 9 in the number system ends at 8, and after 8 comes out to be 10. So this is what we do in the number systems. This is the number system of radix r equal to 9. What happens after 8 is we use the first number along with the place value, which defines that we are moving on to the next set. We are defining a place value, which is essentially a part of number systems theory, and we will be using the intuitive idea we have of that because we are not having that much of time. So this is a radix 9 number system, and we have a octal number system of radix 8, so that ends at 7, and after 7 comes out 10. So this is a number system, duodecimal number system. After 9 we have to define another number t, after that number e, which stands for 11 in decimal, and this stands for 10 in decimal, and this is the 10 of duodecimal number system. And likewise in hexadecimal number system, which we saw how it compacts down the binary into human readable form, we use 0 1 2 3 4, and up to after 9 we just we could use alpha beta gamma, but more compactly we use a b c d up to f. Now f in decimal is 15, and here 10 in decimal is 16. So we'll see the hexadecimal form in a later video or whatever. For now, I think we have had introduction of the binary number system and how addition works, subtraction works, that we can look at. Multiplication and division, in case of that, it would be a mechanical skill to have, but it is not necessary. We could just convert it back into decimal and do all the whatever we have to do, multiplication, division, exponentiation, logarithms and all. We could just do that and convert them back to binary. So for now, we will just have a look at the division, we'll just have a look at the addition and subtraction. So how addition happens in our normal decimal is that, let's say 8 plus 3 turns out to be, but we'll do 8 plus 2 plus 1, where it becomes 10 plus 1, and this is 11, and this is in the decimal number system. So after this let's just talk about some other radix. Let's take the duodecimal number system. In duodecimal number system, 8 plus 3 would be 8, 9, 10, 8 plus 2 plus 1. Now this is not 10 but t. So t plus 1 is 11 in decimal, but in duodecimal it is e. So this is what it turns out to be. We could just look at this, that this is 11 and in duodecimal it is e. So this is what we do. But if it was a larger number, let's just say 8 plus 7, then we could just form till t and e. After that we will have to jump to 10. So what we do is 8 plus 3 plus 4. So this turns out to be e, right? This is 11, so e plus 4. So after e we have a 10, so this becomes e. Just a second, I'll just zoom out. So this becomes e plus 1 plus 3. Yeah, so this is 10 plus 3 in duodecimal system, and this becomes 13. Okay, so this is actually in the duodecimal system, and which is equivalent of 15 in our decimal system. So this is how we do the addition in radix, another radix, that is here it is 12. Similarly, for a radix smaller, there might be some differences for a person who has not done these calculations before. For example, 5 plus 4, let's just say the radix we are dealing with is 7. Okay, so a radix of 7 means that we have numbers till 6 only, and after 6 comes 10. So in this case it will become 9 of decimal, but we do not have numbers beyond 6 in this system. So what we will do is 5 plus 1 plus 3, so this becomes 6 plus 3, and beyond 6 we do not have anything, but we could do 10 because we took 1 from this, plus 2. We took 1 from this, and when 6 is added to 1, we have 10 in this number system. So now we have 12 on this radix of 7. Yeah. So this is how we convert for a radix smaller than 10. So similarly, we have binary. So why binary could look a little bit horrendous is because it gets very large, very long, lengthy for very small calculations. And this is why it is not recommended to multiply and divide using binary. It would be very mechanical and very much prone to errors. So we'll look at binary. Binary starts with 0 and 1, and this is all we have in binary. Beyond this we have to use 10, then 11, then 100. Okay, 101, 110. I think the video editor is video recorder is lagging a little bit. Hold on. Yeah, so 111. Beyond this, I think you could guess it is 1000 and 1001 and so on. So if you can notice a pattern here, what we are doing for any radix, we could go with the other systems also, but it would be very lengthy to write. What we do for any number x, just a second, hold on. For any number x, we write it in the form of radix r, a1 r to the n plus a2 r to the n minus 1 plus a3 r raised to n minus 2 up to some, why is it not working? Yeah, up to some, hold on, up to some radix r raised to 0, so that we have access to odd numbers also, and this would be having the coefficient an. So actually it would be having coefficient n plus 1 if we start from 1 here, because 0 to n, we could start from 0 here, it would be n here, but nevertheless this order does not really matter very much, just to be fine-tuned and precise. Now next thing is, what does this mean is that whatever the radix is, it could be 5, it could be 10, or duodecimal it could be 12, for hexadecimal it could be 16, and for binary it is 2. So from decimal number system, we would like to stay in the decimal number system so that we do not get confused. And when we are using this system, we are writing the radix in this form. For example, for binary it is 2. We are writing the things like this: 2 raised to 6, some number plus 1 2 raised to 5 plus 0 2 raised to 4 plus 1 2 raised to 3, and so on up to 2 raised to 0. So for radix 2, this coefficient never goes beyond 1. It could either be 0 or 1. But for radix other than binary, for example, it could be, the radix could be, if it was 5, then this could go up to 4, because we do not have numbers beyond 4 in the radix 5. And similarly for a radix 7, the number could go up to 6, because beyond 6 you would have to use 10, so it would be one bit above. It would be entering whatever the radixes are raised to 7 and have a coefficient less than r, and whenever the coefficient exceeds r, there would be an increment in the power, and it could be 1 or 2 or whatever the coefficient. So this is what the general method is to convert from decimal to other systems, and it might not be very much clear to you but right now, but you could have a look at the binary number system and conversion just for illustration. So it will make it the things very much clear to you. So we'll find out the, for binary the radixes are right, sorry, the radix is 2, so we'll have to find out the highest power of r which can divide this without creating a decimal, and we can have a decimal basically less than 1, and we don't want to create a decimal which is less than 1, and we have to have some remainder. We may not have a remainder, but we can have a remainder so that we can write in this form, right? We have to then reduce the radix, the index of radix, and then create the create this array, right? So create this series. Okay, so for 9 we have 2 raised to 3. So what this turns out to be, yeah, so it turns out to be 1 into 2 raised to 3 plus, so this is 8, right? 8 plus 1. But if we reduce the radix, we don't have anything for 2 raised to 2, which is 4, and we don't have anything for 2 raised to 1, which is 2, but we have something for 2 raised to 0, which is 1. So this is a least significant bit. We call this as the least significant bit, but this is also very much important. And after this, as we have noticed in any radix, for example in decimal, we write these numbers one after the other as a representation of any quantity. For example, 1024 in decimal is actually 1 into 10 raised to 3 plus 0 into 10 square plus 2 into 10 plus 4 into 10 raised to 0, right? So what we are writing down here is 1024, which is coming down from these. I don't know why it is lagging so much. I hope it is not lagging in the video. So this is the number we are trying to write down, and so this is what we do. So we'll do the same thing here, 1001. This is how we write it. Okay, so this is the normal method, but the problem is when we go along with converting larger numbers, it will be a problem. For example, if we divide, if we have to convert, let's just say 50, let's just say 5000, 5300, 5031, then this would be a problematic thing. It is not very much problematic. We could just go to 2 raised to 12. 2 raised to 12 would be 4096, and we could do with that, but this is a lengthy in terms of notation. We could adopt some other notation which is essentially equivalent to this operation, just that we'll be doing it in a easier form. For example, let's just say we have to convert 1076 into binary 1076. So what we do is 253, we divide it by 2 and write the remainder along with it. So yeah, 253, so write the remainder 0, 2 plus 0. Just a second. Yeah, 2, 13, 4 plus 1, this is the remainder, 267, 0, 236, just a second, this is 1 plus 1, yeah. So here, this is not plus 1, this would be 0, this would be plus 1, and here this is not working. I don't know why this is not working. Just a second, hold on. Yeah, 2, 8 plus 0, then I think we don't have any other number here. My stylus is a little bit blank. So we have to obtain 0 in the division and the quotient. So 1, what the it's not working. It's 2, then we have 0 plus 1. Okay, so now we write down this from down to up. This is the algorithm. Okay, just a second. One zero 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 one one 0 1. I think there is some lag. There's no lag till now. Now it is lagging when I'm actually recording it. There was no lag before I was not recording something useful, but now it is lagging. Yeah, that is it. This is the number, and we could actually try converting it 1076 in decimal and binary, right? 1076 in binary. So this is 1 4 times 0 1 1 0 1 0 0, 1 4 times 0 1 1 0 1 0 0, and that is our answer. This was something we would obtain from the earlier method also. So, and it is all actually the same, just that we are employing an algorithm with a notation. What we do here is that I would like to illustrate with a smaller example. Let's say I would illustrate with 5 or 9. I will illustrate with 9. So what we do with 9 is we write 2 cube plus hold on, I think we write 2 cube plus 2 square, 0 into 2 square, plus 0 into 2. Okay, this is getting out of hand. I think I'll have to continue in another video or whatever. 2 raised to 1 plus, yeah, this is really getting out of hand. Okay, 1, so 8 plus 1. I'll continue just in a while.